Good morning.
Hey.
Hey.
Hello. Hey, everyone. We're going to
Hey,
get
Nifty.
started. Hey, how's it going? Good morning.
Good morning.
Um,
Welcome back.
Welcome back to day 2 of Bitcoin Plus Plus,
Berlin edition,
ecash edition.
ecash
We're
edition.
cashing it in Berlin. Hey, y'all. I hope everyone had a great first day. I think I'm not going to spend too much time chatting this morning. We are running a few minutes. Well, we're not late yet. I think yesterday was a great day of talks and workshops. We've got a little bit more of the same for today. I think tonight we're going to be wrapping up. I think talks end around like 4 or so, 4:30. And then if you guys want to stay here to work on your hackathon projects, we don't have to be out of the building until I think like 8 or 9. So you're welcome to stay a bit later. Drinks are in the fridge. Help yourselves. Is that it? Is there anything
There's
else?
the Shadow Warriors Fedi party from 8 o'clock.
Hey, and rumors have it we're gonna have a DJ and maybe some karaoke around 10 o'clock. So make sure you check that out. So I will be over there tonight. Great. Anything else?
No, we're just introducing our speakers this morning. So kicking off on the main stage planarium here, we have Calvadev talking more about Shopstr. And downstairs, we have Oscar discussing P2P transmission methods. Both the workshops. I hope you learned lots today. Thank you.
Okay. All right. Play. Cool. All right. So this is going to be a bit of like a informal talk. So I'm just going to be going through exactly how Shopstr uses cashew tokens to facilitate payment, and I'll like dive into the code of exactly how we use it in the application and how we like constructed the NIM60 cashew wallet within it. So I guess just to start off, I could just show exactly how like the payment flow on Shopstr is, and hopefully the internet is good enough that the relays are actually connecting. So we shall see. Yeah, everything seems to be working fine. Yeah, so I'm gonna go over here on my phone and essentially, actually it'd probably be easier if I do it like this. Let me, signing out should work. All right, so I'll just be unsigned in. And yeah, so I already have a listing made. It should be this meme for sale. So when I come over here and I buy now, I have two options. I can pay with Lightning. So what happens here is when it generates a Lightning invoice, you pay the payment, it generates a cashew token, and it sends and delivers the cashew token via NIPO4 DM. So you just like the merchant on the other end redeems it, and I'll show that flow. And you have the option to pay with cashew. When you're paying with cashew, you have to be signed in because it's based off of like your cashew wallet that's in the application, and making sure that you have a NIP60 wallet there. Oh yeah, sure. Let's see. See if the UI breaks or not. But yeah, okay. So yeah, here's the payment page. You just set it in person order. So yeah, generates a Lightning invoice. Let me pay this. So yeah, and whenever you're checking out, you don't actually have to be signed in. You don't have to have an Ostra account. Everything. Create an ephemeral key that delivers the cashew token DM. So like, it kind of mitigates a little bit of the metadata leakage. Still not fantastic, but it's a step a bit better than just direct DM. So yeah, once the payment has gone through, it should give you a message that the seller will receive a cash token payment via DM, and I should actually be able to sign in now, and it should be in my messages page. Yeah, so this is like the cash token payment that I received, and yep. So basically, you have two options here. When you claim, you can either redeem. When you redeem, it just pays out to Lightning invoice. When you receive, it deposits it into your cashew wallet within the app and creates a NIP60 token event, and then you can carry that on over to another browser. So here I'll just receive, and then if once it's ready, it'll alert me that it's been deposited. So here it's just like creating the cash token events and then making sure that everything works properly. Token claimed. I come over here to the wallet, and you can see here actually I now have 300 sats. I had deposited 200 sats on another browser. So like locally here, I store like the transaction history. It shows whether or not it was a deposit, a mint, a payment, or it was sent out, and how many sats I had. So here is only 100 sats that I had deposited within this browser instance. So since I have 300, it shows that like it actually carried over into this wallet itself. So that's essentially the payment flow. Merchant scans the QR code, pays, and then they can the buyer scans the QR code, pays, generates a cashew token, gets sent via DM to the merchant. The merchant goes into their DMs, they can claim it, and it's deposited into their wallet. So now you can carry this balance over to any other Nostr application that supports NIP60. So now I can actually like dive into the code, and let's look at all the spaghetti code here. If anyone has any questions, comments, or like anything, just like feel free to jump in. Just let me know. Yeah. So I guess to start off, just the basic functionality of the wallet itself. So obviously, like in the wallet, as you see here, we have you have the ability to just simply receive, send, mint, and pay tokens. So you receive an actual cashew token string, and we only support cashew A tokens. We haven't updated to cashew B yet. You can send tokens. You denominate the amount it sends out, and this whenever you're doing anything within the wallet, it actually publishes a spending history event. That's another thing that I didn't get into yesterday with NIP60 because it's an optional thing. But it allows you to manage state a little bit more effectively. So you can specify where cashew tokens are being sent, which ones have already been spent, and you can use it to more simply handle the actual state, which is probably the most complicated thing, and the thing that I'll actually want some feedback from you guys, because the biggest thing that is actually blocking NIP60 from being merged at the moment is how we handle deletion events, because there's just like the way Pablo proposes it, as I can actually show it here. It should be a NIP60. Redeeming a quote. Where is it? Spending history event. It might be a NIP61 actually. Let's see if I can find it. Yeah, essentially the way Pablo proposes it. So you have your cashew token with your multiple proofs, and whenever you're like, if you've seen a cashew token, it has like the proof amount, and then they're all various denominations. And whenever you're actually spending out, if you're not spending the full balance, it uses partial proofs out of the entire like token that was minted. And the way that Pablo proposes to handle the deletion, you take the proof that was actually used to be spent out, and remove it from the existing token event, and you roll over the remaining token proofs into a completely new event. So and you just delete the other previous event. It can get a little complicated, especially once you have like hundreds of tokens that have been minted and like you're managing all the state. So like one approach that I actually take, which I can get into a little bit. I'll get into it in a second. So let me just start off here. So simply, whenever you're just yeah. I think it's like I don't think it's like the right solution, because it just adds a little bit more complexity, especially if you're not specifying your relay state, because that's something that I've encountered, like especially now that relays have been more of a concern on Nostr itself, like with Outbox and all this stuff. And if you're constantly changing relays or like trying to like fine tune everything, you lose your tokens unless you actually specify a specific set of relays that you're not going to be changing for your cashew token, the cashew tokens you have. So you might be losing specific tokens in different state, and the fact that you have, at least in my opinion, the fact that you already have the existing the original token event, and you can just like check against the mint whether or not it's actually been spent, is usually good enough, and you can have like a larger full state token. That's the approach that I take. Instead of deleting the original the old event, the only time I delete the old event is if all of the proofs within the token have actually been spent. So if there's like partial proofs that have been spent, I don't want to manage that state, because then there's just too many resources being used, especially like on a web application. It kind of like, it's really intensive. Because sometimes you can see whenever you log on to Shopstr, upon first load, you actually don't get your tokens. Once you refresh, everything comes in because it's pretty resource intensive. So yeah, instead of deleting the original event, I like to check that everything. I check all the proofs that have been spent. Remove them client side, and I can create a completely new event containing the full balance. So it's just like essentially like a full wallet state rather than doing like what Pablo does and removing singular proofs everywhere that they're spent. It adds a lot more complexity in my opinion. But yeah, so Ege will also later today is going to be going into Cash UTS. You'll be able to like see like probably I think he's going to work through actually using Cash UTS. But like I personally use Cash UTS and Nostr tools to build everything that has to do with Nostr or Cashew. So yeah, here on the mint button, it's simply calling this request mint API that I just have within here. And literally all it does is creates a new Cashew wallet, a new mint instance, a new Cashew wallet, and then it just requests a mint. And here we're actually storing whenever you generate an invoice on Shopstr, we just store the information just to like show like, oh, how many people are actually coming to check out, testing, and doing all that stuff. And we just store the ID of the event and then yeah, the day, the currency, the hash. Just to verify whether or not the things has been spent or not. And yeah, working with Cash UTS is like it's one of the best pieces of software I know. It's fantastic just to be able to like pay with things. Like because whenever I was first starting with Shopstr, like I mentioned yesterday, Lightning was still a little bit more complicated for me because I was like just barely getting it. I was just graduating at college, so I had no work experience and like no like professional coding experience either. So I was just like trying to like I didn't know how to generate a LN URL invoice, and like I found Cashew and I was like, oh, like I can just create a value and send it to someone over DM. I feel like that's a much simpler solution, especially for someone getting started. And like beautifully, it actually allows you to do a lot more cool things, more so than just like minting tokens and working with Cashew. Yeah, and that's yeah. Requesting a mint is simply these 3 lines of code essentially, and then once like the actual payment is made, it generates a token and returns the token value for you, and you can just like use that, and that's how we deliver the cash token payment. And then let's see. So we mint. Yeah, paying out. Let's see, paying out. Okay, yeah. So when paying out, if you see here in the wallet, if you see here in the wallet, I have like it displays a little balance here. So the way that I'm handling, at least at the moment, it doesn't. I'm not supporting like multi-mint payments yet, but I only display the specific balance you have on the mint you have set as your primary mint. So you can have multiple balances on separate mints, but the available balance for you to spend will only be the one that the primary mint is sent. So if you come here to settings, I think my relay connection might have broken. Yep, my relay connection broke, but okay, it seems to be working fine. Yeah, so like here I have the default mint, so I'm just using the minibits mint, and it'll only display balances that I have on that mint specifically. So yeah, here you see the 300 sats there, and initially here, whenever I'm like handling the actual payout, I should make sure that I'm updated on the correct key set, and that I'm getting the actual balances that I'm able to spend from that specific mint. And I filter the proofs to make sure that they're actually within that specific key set ID. And that you can just simply, with Cash UTS, you can just pay a Lightning invoice simply by just, after the Lightning invoice string is generated, you just pass it into pay LN invoice, and then you just get the proofs that are part of that key set, and you can just pay out. This isn't an efficient way of doing it, because you want to give user a greater coin control selection. But obviously, since this isn't like this isn't like solely a Cashew wallet app, so I haven't gone through like all the nitty-gritty details of making this like a fine-tuned thing. Like probably better suited to be like Cashew.me, or is Nutstash still in development? It's still being used? No, not so much anymore. But yeah, that was initially what I was using when I was working with this stuff. But yeah. So when you pay an invoice using in the manner that I do it, I take all the proofs that are part of the mint. That you have as available balance, pass it through to the Lightning invoice payment, and whenever doing so, when you have change, it returns a change response to you, and yeah, in the case of actually redeeming in the messages themselves, Let's see if I can show it. Oh, now my relay connections died. Okay. Yeah, in the case of redeeming, once it loads, I think I might be able to do it. You have two options. So it tries to pay out to your Lightning invoice. And once it does, you need roughly like a 2% fee reserve whenever you're paying out, because otherwise you might not have the Satoshis required to actually pay out the Lightning invoice and redeem it for sats. So we have that 2% fee reserve, and whatever is left over when the Lightning invoice is paid, the user has the ability to either donate directly to us or just keep it for themselves. Then it gets redeemed as like an actual cashew token itself. So here, whenever you see like the change proofs, it just returns that response. You encrypt the proofs and then send it again via DM to the merchant who's claiming the proofs themselves. Yeah, and in order to like reduce a little bit of the compute intensity, we store in local storage in that session, during that session, and then it's always cleared every time you come out, at least for the token proofs themselves. Other settings like your like theme and the relays and things like that, those are always stored for you. Yeah, so yeah, we essentially just filter that, and then once for any action, so minting, paying, redeeming, spending like on an actual item, and then what was the last thing? Receiving, sending, minting, paying, and and shopping. Yeah, so any of those things we actually store a transaction history amount, a transaction amount, and we publish a spending event, a spending history event. And I can go into the actual code for this. Oh, let's see, should be in master helper functions. Yeah, so spending history event. Yeah, here we go. So yeah, so and when publishing a spending history event, essentially you're just stating within the cash wallet, the NIP60 cash wallet spec, you're stating how the money is actually moving in and out, whether or not it's moving in and out. And this is just to help you if you lose or if you can't fetch specific token proofs, like say you switch relays or for some reason. Well, typically it's only going to be as you switch relays. If like the relay goes down, like you're kind of shit out of luck. You have to. That's an explicit thing that one of the concerns with NIP60 is that like now instead of just trusting a mint, you have to actually trust the relay. But typically that's why you should kind of explicitly state to the user you should be selecting relays that you trust and mints that you trust in order to actually be working with this. Because otherwise, like you're literally trusting money with this, so you have to be actively. You have to be actively stating like, okay, I trust this relay to at least have some state, and that's why it's recommended to either have a personal relay, a paid relay, just to make sure that you have consistency across your wallet states. Yeah, if you can't find, if like the relay is down, like if you have multiple relays and you only published a couple, and maybe you switched and you can't find it, the spending history event actually allows you to reference the event that the original token proof was in. And you can then, if you're missing it, you can then fetch that event specifically and re-enter it into your token balance if you weren't able to find it upon initial load. So it should be, let's see, I think it's clear here. Yeah, my internet is, there we go. Wallet event. Oh, here, spending history event. Yeah, so it's a little bit clear to see exactly how like the spending history event here is used. This is an optional event, as I stated earlier. But yeah, as you see here, it just basically allows you to state whether or not sats were coming in or out, the amount value, and then there's 3 token states: created, destroyed, or redeemed. And there should probably be a 4th, the pending state, because it can actually interrupt and like kind of one thing that you can that might happen on Shopstr, if you've redeemed a token or sent a token out to someone, whenever you come back and reload the wallet balance, you might actually still receive that token in because it actually hasn't been claimed, hasn't been paid out, or hasn't been token swapped because the person hasn't actually deposited into their wallet yet. So there's this helps you manage that a little bit better, but there still should be probably a way to claw back the token if you spent it, but they haven't redeemed it yet. But yeah, and I saw a question over here. Oh yeah. There we go. Yeah, I can see here. So yeah, direction amount, the event, the specific event ID of the token, the relay hint in order to actually find it, and then created, destroyed, redeemed. Those are the things you specify in order for the spending history event. And then here the tag. This is just referencing the wallet event you created in order to be able to find the, as I mentioned yesterday in the NIP60 wallet event, you have to be able to find the mints that you're using, that you specified as a user, that you want to receive cash tokens to, and the relays that you want like zaps to be sent to, or that you want cash token proofs to be saved in. And that was like outlined here. Yeah. So you see here, and the balance and the private key aren't needed in the wallet event. The balance is mainly just there, as I mentioned yesterday, to have an initial state to cash and show to the user, okay, this is how much money I actually have in the wallet, roughly. And then once client side, you validate all the tokens that have been spent, like if they've been spent elsewhere, like you just make sure that you're not like reusing them, and so on and so forth, and accumulate the balance and show it there. But yeah, so that's with the spending history event. And for all the signing, Shopstr supports extension signing, so NIP07, Amber signing, so NIP55, or rather Android signing for NIP55, and just standard Nostr tools signing with your NSEC, which is not recommended because due to the fact that like your NSEC stored in memory, it might get leaked if there's like an attack on the site. But we try to mitigate that a little bit by just whenever like using it, we have it encrypted. So anytime you're signed in with your NSEC, you actually have to input your a passphrase that you originally entered when you signed up for the site. So it's a little bit clunky, which I get is part intentional because we don't want people to be doing that. We want to kind of make it more, add more friction in that sense. But yeah, that's how we handle all those signing of the events. And Nostr Tools makes it very easy and gives you a little bit more granular control compared to like other development toolkits like NDK. It abstracts a lot, but with Nostr Tools, it makes it nice to just be able to actually get a little bit low level and understand Nostr a little bit better if you're working with it. Yeah, so that's the spending history event. And anytime money's coming in, or you're receiving money from a payment, we always obviously generate the token event. And yeah, so whenever we're publishing a proof event, basically just we're doing both the publishing a spending history event in order to record that money was coming in, and we're publishing the token event itself. And again, the token event is rather simple. It's literally just the token proof encrypted within the content, and then it just has the wallet referencing exactly what wallet it's being deposited to. So it's very simple to query. Yeah, so like this is exactly where I'm creating the cash token proof here. And with all of these, wait, what was I gonna? Let me see. Yeah. This is all again just Amber signing. Different signing methods here, just to make sure that it's being encrypted properly since you're using NIP44, and yeah, something to specify here as well. The D tag should be like it shouldn't really be a specific thing. It shouldn't be like in my example, it wouldn't be like a Shopstr wallet. It should just be some arbitrary string, and that's the identifier when using replaceable events. That's an identifier to make sure that you're actually querying the specific wallet. So like one vision that like Pablo has, for example, for using NIP60 wallets is essentially like a blue wallet experience. So whenever you're coming on, you can actually fetch, like you usually fetch multiple wallets. The way that Shopstr handles it, we just fetch the latest one. So the one that has like the latest balance on it. But with you could by filtering out for the D tag specifically, you could have multiple wallets, and then whenever you load up on like Shopstr, for example, you can have some modals like, hey, you have 3 different wallets, each with different balances. Which one would you like to use? And like it just makes it very easy to pick and choose exactly what you're doing. Just like Blue Wallet has like multiple payment wallet options for you to be able to just easily swap between the balances that you want to use. Yeah, and then publishes the spending history event here once it's actually handled. And let's see. So receive, pay, transactions. Yeah. And then for the cashew relays themselves, that is handled with publishing the wallet event. So that should be here. So one thing actually that I was I forgot who I was talking about it with yesterday. Oh, there's one issue at the moment with like relay discovery. So relay discovery is something that's important to consider, especially with the fact that there's only like mini bits is probably the most used, at least that I'm aware of, and we don't want everyone just like joining in and just start using one singular mint, because otherwise it leaves a big honeypot there to be captured. And with the wallet event, it should be the wallet event. With the wallet event, you're publishing alongside the actual state of like what relays and mints to use. You're also publishing just an info event. And typically for Zaps, it's the most important thing. You don't actually need the info event for the normal cashew tokens that you're bringing into the wallet, because you can just reference the normal wallet event. But the 10,019 kind that is used for Zaps, which should be here. 10,000. Yeah, 2019. This just explicitly only states the relays, the mints, and the pub key that you're paying out to. So it should just be like either your pub key or the pub key that was generated out of band. And with this, I was thinking with Greg of StatShoot, we were talking about that you probably use this actually as a way to essentially outwardly show that you trust specific mints, because you're essentially storing if you're storing your life savings on like an IP60 wallet and want to have portability with your balances, you're gonna have this kind of event, especially when you're receiving zaps and all that stuff. And this it's an explicit and manual process of like selecting the specific relays and mints that you're using. So this simple event itself could actually be used to handle mint discovery. Because especially since it's like portable wallet, and you can use it as a bootstrapping mechanism for new users who, like, say for example, I just came in to Nostr and I'm receiving nut zaps, but I haven't established like a specific any of these wallet events or anything. If someone like onboarded me or I follow specific people, I can just query their 10,019s. If someone's trying to zap me a nut information or a nut zap, I can just query some of the people that I follow, their 10,019s, and see, okay, they're using these specific mints. I can just use them to bootstrap to bootstrap their mint balances and just make sure that they actually receive the payments themselves, instead of just having them manually, hopefully finding a bitcoinmints.com and just trying to decide which one they actually trust if they have no information that they otherwise wouldn't have found. Yeah, and when publishing the wallet event, it also goes alongside with mainly it's only handled on Shopstr whenever you're here on the settings, whenever you're actually setting the cashew wallet relays themselves, and when you're setting the cashew mint. So anytime you change the mint or the relays, I always make sure to publish an updated wallet event using the original D tag. So the wallet events are replaceable events. So you can very simply just use the original D tag and just roll over to the new state, and you can delete the old event. You don't have to delete the old event because relays should be handling that on their own. But that's what we do to roll over to new states. So anytime you save those settings, we just generate the event itself. Just basically fetching from local storage the relays that you're posting to, unless you've set cashew relays and those specific relays themselves. Just getting the mint that you have set, or the mints you have set in local storage, and then at the moment we don't give the option to denominate in other fiat values, just sats, but that will be changed in the near future. So yeah, that's with publishing a wallet event. Let's see. Yeah, so on the invoice payment, so the actual delivery of payment, this is a file that I've been meaning to actually like compartmentalize and make a lot simpler, because it's just always bogged down. My AI model cannot even I can't feed it to my model whenever I'm actually working with it. But okay, yeah. So yeah, when handling the Lightning payment themselves, it first creates the invoice, gets the invoice URL, and just generates it, just shows it to the user. So I'm just fetching from the cashew mint and just requesting the invoice data, and I assign it to the invoice, like an invoice state variable, and just display it to the end user, and they can then pay out. So here I'm just constantly checking, and this is something that needs to be updated as well. I believe there's now no longer a need to be constantly querying mints whenever you're trying to check whether or not an invoice has been paid. So like whenever you see here, let me see if I can show it. Yeah, whenever you're coming to an actual payment page, you'll see here in the console, yeah, just for example here, whenever you're paying out, at least on Shopstr at the moment, yeah, whenever you're paying with Lightning, so the invoice gets generated, and you'll see here in the console, it should come up. Seems like it's not. Oh, interesting. For some reason, it's not showing up here. Network, maybe. There we go. I don't know, those are just get requests, posts. Yeah, you can see them coming in here actually. Yeah, here at the bottom. It's constantly pinging the mint to check like, has this invoice been paid? Has this invoice been paid? Has this invoice been paid? And if you go back, it actually continues to do that because like there's limitations with JavaScript that it just continues to fetch, and obviously it's not really great for resources. Eventually, it just like force closes all your relay connections because you're just using too much in the browser. So something to I believe. How is the yeah, you have a question? Oh, okay, yeah. So okay. Yeah, so there's a comment that yeah, you're still asking the mint whether or not it's actually been paid, but it's not you're not you're just checking. Wait, can you reiterate that? Sorry. Yeah, go for it. Okay, yeah. You get the mint quote state without minting. Yeah, web. That's what it was. Yeah. The WebSocket support for it, so that it becomes Nostr essentially, just like communicating over that. Yeah. Yeah. So yeah, once you generate the invoice and it's been paid, so like at the moment it's just constantly pinging whether or not the proofs have generated. Once the proofs are actually made and actually paid out, we just encode them in a cache token string, and we just deliver them over the NIPO4DM. So you see here, I'm just right here. So just awaiting the wallet request. It's just constantly pinging until the payment has actually gone through, and I encode the tokens and then just deliver them here along with like the shipping information and like contact information, whatever's there, if it's been inputted. Yeah, we just capture a little metric here that just shows that how much transaction volume has actually gone through, and it's like displayed here on the metrics page. Yeah, okay, it did load. Yeah, so you see here the actual value, Satoshi value that's actually gone through on a specific payment. Yeah, and sending tokens is very simply just like posting an event on Nostr. It just uses cache Nostr tools there and just delivers it. And this will be updated to use GIF wrap events, so metadata leakage will be kind of mitigated, and it's actually one nice thing about NIP17 DMs, which is a little bit off the cache topic, but because on Nostr the NIPO4 DM is not a very good spec because of the metadata leakage, and it's rather limited because you can literally only send a message content. But with NIP17, you can actually state a subject and reference an event that you're actually replying to. So once that's integrated, once you can like message a seller on a specific item, and you'll be able to actually reference a specific listing and have a filter for only events or only messages that are in reference to the like listings themselves. Because at the moment, when you go here, if you see in messages. So this is, I filter currently for only cash token payments on the order side, and then on inquiries, it's literally all your NIPO4 DMs. So you're just getting, it's like a bunch of other random stuff. See, like there's Michael Saylor who messaged me, and like random people that are just DMing you over NIPO4. But with NIP17, you can actually filter for specific only inquiries, Shopstr inquiries. So then it's like you get rid of all that like spam. Because in the case of like marketplaces and stuff, any message is just spam unless it's related to your specific listing itself. And that's been one of the biggest complaints from merchants themselves. They want an actual way of making sure that every message they're getting is actually in reference to the listings, which is obvious. Yeah, so Yeah, oh, then, yeah, I can show for the cashew payment. So when handling the cashew payment, and I think I might be able to do it if there's a listing less than 100 sats. Oh, yeah, here, cool. So, yeah, so, whenever you're paying with cashew, it just checks. Oh, I don't have a balance in my wallet. Oh, I think I might have. Oh, yeah, refreshing the page, it kind of lost my wallet balance. Oh, no. So with the cashew payment, actually, it won't generate anything. It'll just fetch from your local balance and just pay out directly. So yeah, there's like no like fees associated with it. At least like at the moment. Once like more mints start supporting fee rates, then like we'll have to. That's when like managing coin control will actually be very, very important. So to minimize fees for the end user. But yeah, so whenever handling the cashew payment, create a new mint, create a new wallet. I get the key set again, and I filter for, again, I'm just basically filtering for like the default mint that you have set, and checking that the proofs that are available are the ones that are associated with that mint. And then you just simply Cashew TS has a function that's just send, so that just has the token amount and the proofs that you're using, and it just generates a completely new token with that amount for you, and then again just encode the token and send them over NIPO4. So it's rather simple process whenever just paying directly with Cashew, and then you'll eventually be able to like post the Cashew token string directly, and then it'll just pay out if you don't have any balance in your local wallet itself. Yeah, and then again, we're posting a history event, a spending history event to make sure that you're actually stating, okay, here is the direction that the cash token strings are actually going in, and yeah, any change that is left over just gets redeposited back into your wallet, and we publish the proof event of the new token state that you have. So as I said before, instead of deleting only the proofs you have, the partial proofs that have been spent, I'm actually just rolling over everything into a larger state and then publishing that event itself, and then to store it there, because you still have the other individual token events if you want to reference them whenever working with NIP60. All right, let's see, transactions. Yeah, so this is where I actually handle managing the state of pulling in the Cashew wallets, and this is where it gets like a bit more intensive on the browser side. So yeah, whenever you're with Cashew.js, you have simple filters. Or not Cashew.js, sorry, Nostr tools. You have simple filters when querying Nostr events. So you just have to make sure you have the correct relay set whenever you're querying. So here is the main function you use whenever pulling in Nostr events using Nostr tools. So yeah, so with the relays, on the initial fetching, I just fetch from all the read and write relays, because the Cashew wallet event should actually be published as wide and far as possible. So whenever saving state, we actually blaster the Nostr event to make sure it's actually found somewhere, even if it's not assigned to your specific relays, like your outbox relays. So we fetch from just the general relay list to make sure that we're actually getting like the correct event. It's essentially, it's almost like the 10,019, how it's like a reference for mints and relays, where it should be broadcast widely, and like the NIP65 outbox model, which is the user's specified relay list. So we fetch the wallet event, make sure that it's actually that there is one there, and I then pull in here. This is where I actually analyze like the wallet event itself, and I pull in. Make it a little larger if I can. Oh, let me close this. Actually, I don't need it. Oh, no. Oh, yeah, I can maximize this pane. Yeah, there we go. Okay. Yeah, that's a lot better. Let's see. Should be at the very, very end. Oh, Jesus. Chat messages. I think it would be here. Profile. Where is it? Okay, here we go. Yeah, there we go. Okay. Yeah, so yeah, I fetch the wallet event, and then I'm just like filtering through all the tags, just finding relays, assigning those to your Cashew wallet relays, finding the mints, assigning those to the mints that you have set, and then yeah, just resolving that. And here, the next thing is the proof filter. So I both query for the token events, which are the kind 7375, and the spending history events 7376. Just one to make sure that if token proofs haven't been fetched from the right relays, and I have the spending history event, I can actually verify, okay, this token isn't in the existing set, so I can then add it. Or if the relays, the tokens that I have, one has been spent and I didn't catch that yet, then I can remove it from the wallet event itself. So yeah, so again, just fetching using the subscription, and here if no cacher relays have been set by the end user, you should always default to their NIP60 outbox relays, so the kind 10,002. You got to make sure that you have somewhere to actually be pulling the relays in from. You can't just like hope and guess. So that's why if they have manually set relays, you should just fetch from there and filter for those specific kinds. And yeah, here just simply I don't actually do anything with the content, so like I myself just like once the token proofs are actually deposited, that's when I calculate the balance. I don't show the cash balance at all. I do have it, I do parse it just like in case, like, but there's no I don't find a use for it because you can rather quickly, once the token proofs are in there, just calculate the total value. So yeah, I pull in the token events, unencrypt the NIP44. That is important if you're receiving zaps, because then you need to be able to unlock. But currently, Shopstr doesn't support nut zaps yet. So yeah, on close. So once all the proofs and spending history have been actually fetched, I then check. Okay, out of the proofs that have been fetched from the proof events themselves that have been fetched from the relays, which of the proofs have been spent, and I only delete the proofs if all of the I'll only delete the proof event if all of the proofs contained within that proof event have been used. So rather than following like the proposed token deletion protocol that's in NIP61, I like as I explained before, I handle it by just rolling over into a larger state and deleting only if all of them have been spent. Because you can still like check whether or not, okay, has this, you can check against the min, has this been spent or not, and I can then just not include it in the new event. So yeah, it just filters for any spent proofs. Just simply check proof spent against the wallet and verify there. And I'm only verifying against the default mint. So if there are other tokens, I just don't like manage them at all. I just don't add it to the existing balance. So yeah, and then I then filter in with the spending history. I then filter to make sure that are there any proofs that have been are in the out direction and in the destroyed direction, or in the destroyed category, just to verify. Okay, this is one that has gone out and it's not usable at all anymore. So you filter out for those proofs, which I then compare against the existing like wallet state. The proofs that are set there and filter them out here. So yeah, I just assign the new cacher proofs to the filtering of the destroyed proofs, and all that will be left over is non-spent proofs. And yeah, and then I then also filter for incoming proofs, and yeah, I then filter for incoming proofs, and if there are any proofs that have not been added to the current existing wallet state, I then add them back in. So yeah, here you can see that I just I filter out for the out proofs and the events that are not included within the outproof IDs. I then added them to the it's moving a lot. I then added them to the proofs to add back, and then I didn't filter to make sure that the proof events are not aligned in the existing wallet state. So I have the full wallet state. Are the proofs in there? Do they line up with the ones that are coming in? If they are, then I don't do anything. I don't add them in. But if they're not, then I add them into the existing proof state. And yeah, that's the updated the wallet state for you. And then your wallet balance should be updated locally. Yeah, and then at the very end, any proofs that have been fully used or any events that have been fully used, I just delete them, request deletion. And on Nostr, people say that it's not super reliable. Deletion isn't super reliable. But from my experience, it's been quite reliable, especially with like most posts on Amethyst. And if you just blaster the deletion requests, like usually you can't find it anymore. Unless obviously a lot of apps now are like local, trying to be local first, so they cache a lot. That's the only instance where the deletion events might not actually work. That's one reason actually why on the client side I wipe the wallet balance before fetching everything. Otherwise, like there might be like duplicate state, and you might be like trying to double spend tokens that you don't actually have. yeah. Let's see. Yeah, so I've gone over how we're fetching and handling the wallet event, how we're requesting mints. This, I believe, is just the wallet, how it's actually handled here. Yeah, and like here, this is where I shows where I locally just calculate the wallet balance itself and just set it. And it's constantly pinging the local storage and checking like, okay, is there new tokens that have been come in, and then it just displays the balance itself. Yeah, and then preferences, that was the settings, and then there, that's where we publish the wallet event. Payment. Transactions. Yeah, the transaction history. This was like basically somewhat taken from Nutstash, how they handled it. Except I didn't include the proof event because I didn't want to associate it with a specific token. So I'm just stating like the specific. Whenever I store it locally, I'm just stating the type that it was. So like again, like the 5 types were receiving, sending, minting, paying, and then shopping, and then it just displays an info for it, the little icon for it, the amount, and the date that it happened. And if whenever you using NIP60 as you saw, if there's no if you are just fetching in new tokens, and you didn't do that in that state of the browser, it won't have that transaction history there, so you know exactly how much balance was from external wallet or from external NIP60 wallet. And then yeah, so sending, sending also it just simply uses the that cache TS function for just send. So sending again just passes in the filtered proofs. Yeah, it just passes in. I filter the proofs to make sure that the key set is actually the proper key set is being used, and that the proper tokens are being used, the value that you want, and then it just send generates a new token, and then you just encode it and send it over DM. And yeah, and that's one of the great things I think about because cache is just text, you can just simply render it as anything you want, which is even though it's rather simple, it's pretty powerful because you can like render it to your grandma or a relative of yours who doesn't really know what sats are. You can render it as a fiat denomination and like literally you let it look like a little dollar bill, like it is in like Boardwalk Cash. It's like even it's simple, but it's really powerful. I think. Yeah, and then receive button. So when receiving, here. So when receiving, since we don't support CashewB, just CashewA. I'm on like the older version of CashewTS. So I decode the token, the Cashew token string, and then from it you can extract the mint and the proofs that are being used. And I just check whether or not they're actually being spent, or rather whether or not they have been spent. And if they haven't, then I just continue through and I filter for making sure that they haven't already been added to the wallet state. Because double spending is somewhat possible on Cashew, you can, I make sure to not allow, if you already have wallet balance locally, I don't allow you to add anything back if the proofs match. Just like a little filtering mechanism to try and prevent that as much as possible. Yeah, and then it just checks whether or not there's duplicate proofs in here, and returns just the greater wallet state. And whenever that's done, it just publishes the wallet event itself with the updated cached wallet balance and the proof event of the full wallet state here. So yeah, just assign there. And the spending history event to show that you actually received money rather than something else. Paying button. So the paying, this is where you pay out to just a Lightning invoice. We're gonna have camera support and then just paying out to LNURL soon, like within the wallet itself, because we already pay out to Lightning addresses within the messages themselves. So whenever paying out, I just again filter for the correct proofs, pay the LN invoice, and it's very similar to just paying with the Lightning address, and yeah. Getting the response there. Mint button, invoice card. Let me show the messages because this should have the redeem, I believe. Decrypted, encrypted, content. Handle send message. Handle send gift wrap. No, that's new stuff. Let's see. Oh, it might not be here. Redeem. Let's see. Oh, I think I should know where it is. Let's see. That should be somewhere here. Claim button. Yeah, here we go. All right, so this is where we handle the LNURL redemption once it loads. Yeah, it's the one issue with cloud IDs. Like if you need internet, you need good internet. Let's see. Yeah, essentially, we're just using Albi tools here. If I remember, yeah, Lightning address, the Lightning tools that Albi has, just to make it simple. One for currency conversions, because Shopstr actually supports 160 currencies, I think. So you can just like denominate in whatever currency, and then it'll give you the exchange rate in satoshis whenever it gets the payment gets delivered. Yeah, and we also use that to generate the Lightning address invoices from the end user who's receiving who's redeeming the cash token payment. So yeah, so receiving this is the right one. So yeah, so this is the state where we handle whether or not you're actually depositing it into the local storage. To the local wallet storage. And we just again, whenever receiving, we check that the proofs have not been spent, filter them, and then just make sure that that there's no duplicates, and then we publish a proof event to make sure that it's actually stored on your relay and published out, broadcast, and a spending history event, and an updated wall event with the new cash balance. And when redeeming, here is where we just using Lightning, the Albi tools. You just generate a new Lightning address based on the URL, the LN URL from the kind 0 metadata on Nostr. So if you want to get any profile information from a user, you fetch a kind 0, and then their Lightning address should be stated in the LUD16 field, and you just pull that in. And across the app, we use context, so it's like context hell on the application. You're just like fetching in and like making sure that the states are set on the initial render, and then you can just pull in anywhere in the application to make sure that you're getting the right information. So yeah, I'm pulling in the LN URL from the kind 0 metadata, and then just fetching an invoice, generating an invoice, rendering it, and then or not rendering it rather, just fetching a new invoice, paying out, and using the PayLN invoice function from cache.ts, and getting any response change. So here, the change proofs, whenever you're paying out to your wallet, checks, okay, has it been spent? Has it been spent? Get the change, and then you give the user the option to actually redeem or deposit it. So let's see if I can actually do that here, because it's not been loading. Let's see, 1 second. Okay. Once my messages load, should update. Yeah. Okay. So here, claim, redeem. Let's see if it goes through, because I redeemed it to my wallet, so it might not actually be available. So redeem. Once it goes through, yeah, it's fetching the invoice and then paying out, attempting to pay out. If there's not enough balance, then, or if there's not enough tokens here, then it might not go through. Otherwise, it defaults if you're unable to redeem, because we assume that if you're unable to redeem, that you do not have a Lightning address set up. It just deposits it into your wallet immediately, so it just saves state there. Let's see, connection might have crapped out here. Nope, seems fine. Let me try this again. There we go. Yeah. So here we go. So when the token redemption fails, it just deposits it into your wallet itself. Gives you an info message there, and then it should and because of the fact that we're filtering for unspent proofs, no wallet balance update happened because it was already saved locally. But yeah, I think let's see if I can actually. I don't know. I did not try this, so let me see if I can actually port it over to Highlighter and load here. So let's see if I can show that the NIP16 action on a different application. If I have good enough internet to do this. Okay, so Highlighter loaded. So Highlighter is Pablo's client, which is a long form like content client for Nostr, and he built in a NIP60 supported wallet. So whenever creating a wallet on Highlighter, you should be able to fetch from. You should be able to fetch it actually on Shopstr, so you'll be able to use it locally. But I am not sure if it will go the other way around at the moment, because you might be filtering solely for specific types of D tags in the events. If it loads, let's see. Oh, I don't think it loaded at all. Yeah. Let's try nutsack. There we go. Okay. So I think keys wallet. It can be not very stable. Definitely not. Let's see. Yeah, it's seeming like these are the only ones that are actually lnw.cash. Let's see, I'm just like shilling these other projects that are supporting it at the moment, but due to latency issues, I'm not sure if I'll be able to actually show them. Yeah, I think it's taking a little bit too long. So yeah, that's essentially. I'm pretty sure I covered basically everything there. And then yeah, and another thing, I guess, when actually fetching the cache wallet stuff, I do not allow if they're signing with an NSEC, because of like the bit of the clunkiness and having the NSEC stored in memory. I try not to allow the user to really actually use the cache wallet itself. Like it's there, but with signing with an NSEC itself, it's not as reliable due to the fact that it's constantly requiring the NSEC, and you have to consistently keep inputting the passphrase whenever actually querying for the token events. So you might not actually be getting it'll constantly be pinging, and you input the passphrase, and like the relay connection might actually time out with a long enough time frame. Yeah, so here they again just call the cache wallet itself, and then again I filter just like one last time, making sure that there's an actual values within it, and then just store it locally. Yeah, that's essentially it. Yeah, so basically went over how Shopstr actually pays out using CashUTS. And it's a fantastic library if you're working with TypeScript and like just you trying to play around with Cashew, especially if you just go to their documentation, you see how like small it is to just mint a token and pay out and like start using it, and how we deposit and handle cache token encryption, how we store it locally, and use NIP60 to save state across the wallet. And it was actually NIP60 came at a great time because when I was developing Shopstr, I was solely relying on local storage at the time, and I had a couple merchants who were actually, for some reason, I did not know people even did this. They were shopping and like using like the pop-up browser that comes up whenever using an application. So like every single time they would close out, they lost state every single time. So they just had to constantly be re-signing, and I was like, oh shit, like your wallet balance is not going to be there whenever you redeem. And they were redeeming to their cash wallet balance. Thankfully, they had like backups, and like you could still like access your messages and claim them again. But yeah, due to that, I was like, oh, I need to find a way to actually have a good backup way, a good way of backing up your cashew tokens. And NIP60, I was like talking to Pablo, and then he like came up with the idea, and it was fantastic timing to be able to actually handle that state. So now you can actually carry over your wallet balance and like have at least somewhat okay reliability when it comes to making sure you have your balances where you want it to be. But yeah, if there's any other questions or you want me to like kind of clarify something or go back to a specific piece in the code, just let me know. Yeah, yeah.
Can you talk about how the new merchants are onboarded in terms of setting up their wallet and picking a mint for them?
Yeah, so by default we use the mini-bits mint, but I'm actually after thinking about like the declaration of the 10,019, I'm actually gonna start using that to bootstrap. So like if they're a new merchant but already have an Oster following, or they follow people on Oster, I'm gonna be fetching their 10,019s of the people they follow, and then using that, like basically filtering it, compressing it down, and only using like essentially like a web of trust. You can specify like, okay, I want at least 3 people to be using this mint that I know in order to decide whether or not I want to use it for my own. So that'll like bootstrap it for them. If they don't have a following on Oster, then I'll just be defaulting to the mini-bits mint. But Shopstr, I'll actually be spinning one up for Shopstr itself with some liquidity and like probably using that, because most of the transactions here on Shopstr are usually around like $20 to $70 whenever they're made. So like, it's like in that rough range. So that's like and it's not too frequent. I think Shopstr's facilitated around like 5 million sats worth just on Cashew alone. And then like out of band, like there's been like a few million as well that are just like not using our payment thing. But yeah, to bootstrap the merchants, use the 10,019 as a reference because it's like basically like a manual attestation. And I feel those are very powerful, but they're very clunky unless you're like a person who's like already somewhat used to like, oh, okay, like manually going through relays and everything. It's a nicer way for a new user to get onboarded. Yeah, or just default to mini bits, at least for the time being. We're gonna probably have more dynamic once multipath payments come out actually, or once it's like more supported on Cash UTS. I'm gonna abstract away probably the usage of Mint completely and just distribute it to as much as possible, to as many mints as possible, and like allow like reserves and allow them to like granularly decide, okay, how much I want in specific balances. So that'll be how that's handled eventually. Yeah.
Right now, you're not you're not actually looking for a common mint for the payer and for the sender of payment and the recipient, right?
No, yeah, we actually whenever because like the mint information is included in the encoded token, you don't actually have to have a common mint. You can just redeem, and then if you're redeeming into the wallet, it'll be saved in state with the mint that is specified in that token. So you'll still be able to access it from the mint that the sender minted it on, or if you redeem out, it just pays out to your Lightning address. So it's not you don't unless the user themselves wants to use a specific mint, which we haven't allowed for yet, like you said, then there's no need to handle that because in most cases they redeem and aren't currently like holding the balance because like for good reason, right? Because it's still pretty like a niche technology, but it's eventually being able to swap into a trusted mint will definitely need to be considered. Oh, he's got one.
I'm just curious if Shopstr is using deterministic nuts or no.
No, it is not using deterministic nuts. Yeah, not yet.
Oh, is it on the roadmap or?
Yeah. And same with pay to pub key.
All right.
Yeah, pay to pub key nuts. Those will be great too, because one friction at the moment when actually paying out, or when getting paid for at least for the buyer, if they already have like wallet balance and stuff, you might want to pay with you sometimes might want to pay publicly. Like some merchants might want that. So having like a Zap payment would be fantastic. I don't like the normal Lightning Zap spec that much, but with with Nut Zaps, you can just like lock it publicly and show like, okay, I paid 100,000 sats for this like I don't know shirt or whatever, and like the merchant can show like they have like actual validation that like, okay, there's an actual verifiable payment spend, and they can show like, okay, there's other merchants that are there's people that are actually using this and people that are buying their goods, so they can like broadcast that to the network a little bit more. All right, if that's it, thank you guys very much, and yeah, I'll give you back like the last 15 minutes here.
look right. Yeah.
So take it off, flip it upside down.
Okay, I knew something was wrong. There we go. Feels better.
And then look at me. Can you mute it for me?
We were close. Yeah, we have time. We have time. Yeah, you can.
Had it was okay. It wasn't the opposite of whatever that is. It certainly wasn't insulting in my head. Apologies if it came. No, no, but it wasn't. It wasn't meant to be. It wasn't meant to be a joke. I apologize for that. All right. Ready? Ladies and gentlemen, welcome back to Bitcoin Plus Plus. Many of you know Alice. She does lots of Lightning payments. You've probably also heard of Bob. We have him here to do a talk. This is awesome payments, social AI, and stablecoins. Bitcoin Plus Plus. Thank you.
Hey guys. My talk is titled Awesome Payments. Before we dig in, first my background. I'm Bob. I've spent the last 10 years in payments. First in traditional payments, investing in fintech and payment platforms. Then at Strike, working on Bitcoin and Lightning payments. And now as the founder of Boardwalk, focused on using Nostr and ecash to advance Bitcoin payments. And I'm going to talk today about awesome payments in 3 very fast-growing markets: social media, generative AI, and stablecoins. I'm going to describe how ecash helps us capture these markets and enable awesome payments with Bitcoin. Awesome payments are more than just simple payments like paying for a coffee or making a purchase online. They need to be awesome. They need to be incredibly fast, highly scalable, programmable, and much more, which I'll talk about today. And this is important because I believe awesome payments is how we onboard the next billion Bitcoiners. And I believe that Bitcoin payments is the only way to enable these markets in the future. But first, let's start with awesome consumer products. These are the three biggest internet consumer platforms of the last 30 years. The internet browser, the smartphone, and AI. And they all have created incredible consumer products. However, for much of the history of the internet, monetization and consumer payments has been ad-driven. So the internet payments experience looks like this. These are display ads. Or like this, ads and feeds. Or like this, ads pop out of nowhere, and you can't figure out how to close. But fortunately, there's been a huge shift in online payments over the last 5 years, and the internet is now monetizing more than just ads. Each of these payment platforms has undergone a huge change in the way payments are distributed, and there's now an opportunity across all three to create better payments. Global payments are actually happening on the internet rails. Social consumer P2P payments are happening on mobile, and AI payments are just growing really, really fast. So I'm going to talk about each of these opportunities and how we can use them to create awesome payment experiences with ecash and Bitcoin. We'll start with social peer-to-peer payments. This graph is TikTok's payment volume of tips and gifts sent peer-to-peer over the last 5 years. They did less than $1 billion of payment volume in 2020. And next year, they're expected to do more than $9 billion of payment volume across their 1 billion users. And this is just TikTok. Combined with other social platforms, there's well over $10 billion of peer-to-peer payment volume expected next year. TikTok social P2P payments are gifts that users send to other creators or other users. There are roughly 120 fixed value gifts. Users buy coins that they purchase on their phone with Apple Pay, and creators receive diamonds that they can cash out to their bank account. The gifts range anywhere from 1 cent on the lower end, if I send you a rose, or upward of $450 in value on the upper end. And they're shared in live videos between fans and creators. And it's a huge revenue driver for TikTok. They actually take a 50% take rate. And so not only is it a huge payment volume driver, it's a huge revenue driver. And they do an amazing job. It's highly gamified. You can set goals. So if you want to receive, in this example, the creator wanted to receive 1,000 gorillas, they have 4 hours to get 1,000 gorillas. There's leaderboards by type of gift. There's leaderboards by how much gifts you have received and sent. They have exclusive gifts. They have badges for you when you send certain gifts. There's levels, so you can level up and receive and unlock even more gifts. And then finally, there's rewards. So if you are in the top receivers of gifts, they'll give you bonus rewards in gifts. So they really do an amazing job, and that's why the growth has been incredible in the last 5 years. Of course, it's not just TikTok. On Nostr, you're seeing the growth of Zaps. Facebook and X are also experimenting with their own versions of P2P payments. So social P2P payments is a massive and growing opportunity for us. Next is AI payments. This graph is OpenAI's consumer payment volume over the last 5 years. It went from 0 in 2022, so 2 years ago, it was 0. They'll do almost $3 billion of payment volume this year across 200 million users, and they're expected to do more than $10 billion of payment volume next year across almost 500 million users. This is just an insane graph. But today, AI payments looks like this. You pay $20 a month to OpenAI, who processes the payment via Stripe and the traditional card networks. But there's almost no way, if AI does what we think it's going to do, this is how payments will work in the future. There's zero chance. Very soon, it might look like this. So this is an AI agent. And an AI agent has no ID, and they have no bank account. And there will be hundreds or thousands or millions of them. And these agents will need to acquire certain resources. They'll need to acquire data, training, inference, compute, pay for other tasks. And these agents will need to pay other agents directly, who will need to pay other agents, who will need to pay other agents to accomplish their task. And so these payments, they need to be instant, cash-like, programmable payments. These are computers paying computers. These payments are expected to happen on a truly unprecedented scale. So this here is a graph of spending on cloud CapEx by the big four: Microsoft, Google, Amazon, and Meta. They increased CapEx spending $70 billion this year, and they'll do over $200 billion of CapEx spending next year and likely every year in the future. This is an outstanding number. To give you a sense of scale, that is the spend equal to the market cap of the 37th most valuable company in the S&P 500. So the 37th most valuable company's market cap is equal to the size of that spend, which is McDonald's. So these companies are now spending a McDonald's amount of cash every single year on cloud and AI infrastructure. But it gets crazier. In the US, we're restarting nuclear power plants to make AGI a reality. In the latest deal, Microsoft will be helping restart reactors at 3 Mile Island, and each reactor costs about $10 billion a pop. So we're spending $200 billion annually plus $10 billion on every new reactor. This means that there's likely trillions of dollars of payment volume expected in the future, and it's a huge opportunity for us. And finally, stablecoins. So this graph here is estimated stablecoin volume. It's kind of hard to estimate, but I think it's pretty clear that there's certainly at least 50 million users globally that have used stablecoins, and the volume is somewhere between, say, $5 and $10 billion this year or next year, and it really, really accelerated starting in 2022. So it was almost nothing before 2020, and now it'll be easily $10 billion next year or the following. Stablecoins provide stable value. This is especially important in economies that have poor currencies. So on the chart on the left, you'll see consumer crypto volume in Argentina. 58% of the exchange volume was stablecoins. And on the right is the greater Latin American region, so Argentina, Brazil, Colombia, and Mexico. And even there, still 30% of consumer exchange volume was stablecoins. And you can see why they prefer stablecoins in Argentina. The peso lost 63% of its value year over year. And unfortunately, Bitcoin's not very stable. So Bitcoin itself lost at least 1% of its value 105 days over the past year. So Bitcoin is still too volatile for this use case as well. And people don't like volatility. I think it's helpful to walk through a couple of examples of why stable value is really important in some of these markets. First, the remittance example. The example here is a domestic worker receiving his salary. He uses that to buy a stablecoin. He sends that as a remittance to a foreign family member who is then able to use that stablecoin to buy goods and food. That whole process, that takes about 1 to 3 days. So any 1% change in the value of a coin would be detrimental. And these people, they're not like speculators or risk takers. They don't want to take volatility risk. They just want to buy a fixed basket of goods, and they need stable value to do it every week. So very simple. So stable value for them is valuable. And now we'll look at another example, which is merchants. You can see here we have a consumer buying food from a merchant. They check out, they pay with stable coins, And then the merchant accumulates these stablecoins and uses them to pay their employees and restock their shelves. That process takes anywhere from 5 to 30 days, and merchants operate, especially grocery stores, on a really, really thin margin. So a 1% move can wipe out a merchant in a day or in a month. And even the best grocery stores operate about 1.5% margin, which is Kroger's margin. So these merchants, they're not risk takers or speculators either. So stable value is mission critical for them. They can't afford volatility. And this is one of the reasons why you've seen stablecoin volume explode over the past 5 years. It's also a huge opportunity for us. So now across social, AI, and stablecoins, there's at least $100 billion of new consumer payment volume coming online in the next 5 years. And this payment volume is distributed, consumer-driven, advanced technology-based payment volume. And it needs payment technology that can facilitate transfer of value. And these new products, they touch on some of the most important aspects of our lives. Free speech, actually open AI, and global payments. Traditional payments, the rails, they don't work well. They're slow, they're expensive, there's high fraud. Traditional payments need decentralized because they require massive teams, human intervention, legal arbitration. But we can do better. We have internet native money. So how would we design internet native money for payments specifically, for these specific markets? What would that look like, and what would the important features be? So now I'm going to walk through some of the key features of how we should design internet money for payments specifically. Internet money for payments would have instant access. It would be permissionless. It would be virtually free to use. There would be no information required. It would be fast. There'd be no chargebacks. It would settle instantly. It would be highly scalable. It would be everywhere. So it would work globally, but also it would work anywhere, including offline. It would be programmable. You'd be able to send multi-party payments, conditional payments, and more. It would be multi-currency. You wouldn't have to take FX volatility if you didn't want to. It would be private. Both amounts, senders, and receivers would have privacy. It would be liquid, so it would be easily exchangeable in any market. And it would be trustless. So you'd be taking no counterparty risk. So this is the rough rubric for grading the success of an internet-based money for payments. Fortunately, we have internet money, we have Bitcoin, and we have Lightning. So let's start by seeing if these protocols will work for these new awesome payments. First, we'll do Bitcoin on-chain. Bitcoin on-chain is not instant. We know it takes about a 10-minute block time, and you need a Bitcoin on-chain address. It's not fast, again, 10-minute block time. It's not fast enough, certainly for these markets. It doesn't work everywhere. It's global, yes, but it doesn't work to send offline. Its programmability is very limited today. It's not multi-currency. 1 Bitcoin equals 1 Bitcoin. It's not private. It's relatively limited. It's a public blockchain. But it is liquid. So you can trade Bitcoin anywhere on hundreds of exchanges in any country in the world. And of course, it is trustless. And this is one of the most important aspects as Bitcoin, as money. But in the context of internet payments for these use cases, it's not great. It fails as internet money for advanced payments. And so now we'll do Lightning. Does Lightning provide instant access? No, you need liquidity, you need to KYC if it's custodial, and then once you do, you still need a payment identifier. You need to tell the person where to send the money to. Is it fast? It's faster and improves on things like paying for coffee, but you can't send hundreds or thousands or millions of payments in 1 second on Lightning. It's not fast enough for the use cases that we're talking about, for these new markets. It works globally, just like Bitcoin, but again, you can't send offline. It's more programmable, but still pretty limited today. It's getting to be multi-currency. So there is taproot assets, but today it's not, so I'll mark that as an X as well. Private, there are improvements to privacy on using Lightning, and of course it is improving, but it's not private enough, and certainly not if you're using custodial Lightning. And then this is an important point. It is liquid because you can exit to the main chain. You can trade Bitcoin. So it is tradable everywhere in the world because Bitcoin is the base layer. And then similarly, it's sufficiently trust minimized because you can exit to the main chain. So this is what Lightning looks like. And if we combine Bitcoin on chain and Lightning, you can see we know Lightning has improved Bitcoin payments, but not for the specific markets we're talking about today. For the next generation of consumer products, it's not enough alone. So for these new markets, Lightning has limited improvement in capabilities. And so now we get to do ecash. Does ecash provide instant access? Yes, it's a bearer message. Is it fast? Yes, you can send thousands of payments instantly. Does it work everywhere? Yes, it works globally and it works offline. Is it programmable? Yes, you can do things like multi-party payments, pay to pub key, and eventually conditional payments. Is it multi-currency? It already is today in Bitcoin, dollars, and euro, with more coming soon. Is it private? Yes, it uses blinded tokens, and in fact, there are no users or accounts. And then these last 2 points are very important. Is it liquid? It is liquid because it's convertible down into Lightning, which is convertible down into Bitcoin. So you can exit to Lightning and exit to Bitcoin. Similarly, is it trustless? We all know holding ecash is custodial, but at the point of sale, when we're talking about payments, it is trustless because it's interoperable with Lightning at that point of sale, and you can exit to Lightning, which you can exit to Bitcoin main chain. So at the point of sale, it is a trustless transaction. You don't have to give someone the good or service unless you trust the payment. So this is ecash. And now, if we combine it with Bitcoin and Lightning, the combination of Bitcoin, Lightning, and ecash is an awesome payment system. And this is an extremely important point. It needs to be all three. It has to be Bitcoin, Lightning, and ecash. Ecash does not stand alone. And importantly, when one of these gets better, they all get better. So now we have the tools to go after this $100 billion of payment volume and $1 billion new users market. And awesome payments is how we onboard that next billion Bitcoiners. So now I would like to show the early ways that Boardwalk and ecash more generally is going after these new fast-growing markets. First, a quick overview of Boardwalk. Boardwalk is a Bitcoin payments platform that integrates ecash and Nostr. We're using ecash because we believe it's the best payment experience for these advanced markets that we're talking about today. So I'm going to show how we're using ecash to serve these markets, social, generative AI, and stablecoins, and accelerate Bitcoin payment adoption. We'll start with social peer-to-peer payments, which is this graph, so $10 billion plus. And what I'm going to do is I'm going to look at two of the most important features of each of these markets, and then talk about how ecash improves the payment experience. So for social peer-to-peer payments, we're going to talk about instant access and multi-currency. And this is our example gift, the Bitcoin guy. ecash provides instant access. It's a bearer message. So you can send ecash money in the message on any social media or messaging platform. There's no identifier required, so you don't need to know my handle, or you don't need me to send you an invoice. You can just send me ecash without ever asking me for anything. There's no liquidity required, so there's no like sender or receiver liquidity. You don't have to worry about payments failing. It just works. And then finally, it's cross-platform. So on the top there is a ecash token. That's a pumpkin. That's posted on Twitter. At the bottom here, that's a teddy bear ecash token posted on Nostr. It works cross-platform. So this is an ideal experience for creators and peer-to-peer payments. One account that works across the internet with no platforms controlling the on and the off ramps. And then multi-currency. So most users just want to use their own currency. Some want Bitcoin, most want dollars or euro or their local currency. And we can provide that to them with ecash. And that's what we've done at Boardwalk. We currently have 2 balances, both Bitcoin and dollars in the app. Okay, AI payments. So this is one I'm really excited to talk about. And that's why. So AI payments, they need to be fast and they need to be programmable. These are computers paying computers. First is locked ecash. So this is one of the simplest forms of programmability and already used in almost every wallet in the cashew space. It's also known as pay to pub key. This is where you can lock ecash to a specific pub key and only the user with the corresponding private key can unlock the ecash. So this is the kind of first and simplest form of programmability. But that allows you to already do some pretty cool things. So that allows you to do things like split payments. So here we have the AI agent paying R2D2 and vendor at the same exact time, instantly. And this works whether you're paying these 2 agents or 1,000 agents. But it's still early for agents. So I wanted to show an example of how we're using split payments actually today. We're currently working with independent designers that are using GIFs to help monetize their art. So for this example, a user can share this hermit crab gift on Boardwalk, and we can instantly split of the 5,000 sats they send, 4,000 can go to the recipient they're sending it to, and 1,000 sats can instantly be split and deposited in the artist's account, and that can happen automatically every time. And then finally, conditional payments is early, but you can imagine the Mint providing Oracle services and processing DLCs. There's no additional trust required. You're already trusting the Mint with the strongest form of trust. They have your money. And so they are able to process additional services on top of that. And conditional payments allows AI payments it will allow them to be made based on the type and quality of information returned by agents. And then it also enables other interesting markets like betting and futures contracts, which could also be integrated into that system. Next is fast. So ecash is a database. That's great. It enables millions of payments to be sent at the same time with no blockchains, no consensus, no hops, no rebalancing. One example of what's possible is a very powerful example Callie shared a few months ago, and I wanted to walk through it. In this example, a user wants to pay a VPN service per kilobyte of use instead of with a monthly subscription. So it starts with the user paying 10,000 sats via Lightning to a Mint and receiving back 10,000 1-sat tokens that's locked to the VPN provider's public key. Now the user has these tokens and can stream the tokens to the VPN provider for every kilobyte of data that they use. The VPN provider is able to check the incoming token signature, and they know it can't be double spent because it's locked to them. And at the end of the week, the VPN service is able to unlock the cash and redeem the Bitcoin. And this is the crazy part in that example. In that payment flow between the user and the VPN service, there was no Mint, there was no Lightning, and there was no Bitcoin. So no Mint is even needed to be involved in that payment flow. The Mint just is involved at the beginning to lock the ecash and at the end. So 2 Lightning payments and potentially millions of payments between the user and service. And this is one example of what's possible, and it's very unique to ecash specifically and can be highly, highly scalable. And finally, stablecoins. Which is this graph. So two of the most important aspects of stablecoins is they need to work everywhere and they need to be liquid. Everywhere is actually, it's pretty simple. They have to work globally. They need to work offline to receive money, and they need to work offline to send money. So when you go to a market on a Caribbean island that has no internet, you can still buy your groceries. And they need to be liquid. So like I mentioned, ecash doesn't work without Bitcoin and Lightning. And this, I think, is one of the most obvious examples. With ecash, you get the Bitcoin network effect. So we don't need to go rebuild exchanges and payment rails from scratch. Ecash gets the full benefit of the Bitcoin network effect. So let's walk through an example with Boardwalk. In this example, a Boardwalk user in the US sends money to his friend in Mexico. And to do that, he first loads $100 via himself, an agent, or an exchange into his Boardwalk wallet. So he has $100 of ecash in Boardwalk in the US. He's able to instantly send that money as Mexican pesos received in his friend's Boardwalk account in Mexico. So the friend in Mexico receives 1,900 Mexican pesos instantly in Boardwalk in Mexico with no volatility in exchange. The friend can then go to a Bitcoin agent or a Bitcoin exchange and receive 1,900 pesos in cold hard cash in his hand. And this is leveraging the fact that there are already Bitcoin agents and exchanges in virtually every market in the world. And importantly, the friend in Mexico just receives and uses pesos. He has 1,900 pesos in his Boardwalk account, and then he gets 1,900 pesos of cash in his hand. There's no volatility. There's no exchange rate involved. There's no dollars. There's no Bitcoin. He just gets pesos into Boardwalk and then pesos into his hand. And for the Bitcoin exchange, it's just Bitcoin to them. So this is the powerful aspect of the network effect, is the exchange doesn't need to know anything about Boardwalk. They don't have to know anything about Cashew. They don't have to know anything about mints, and they don't have to know anything about the user. They're just taking in Bitcoin and exchanging it for pesos like they do every day. And this can be done well below half the cost of traditional remittances. The fee is just the fee to buy and sell Bitcoin, which can be anywhere from 1% to 3%, versus a traditional cost of remittances, which can be well over 10%. And it works for not just remittances, but for the merchants' use cases as well. So that's how we build awesome payments. And I think that's how we capture the next billion Bitcoiners. We build cross-platform social payments, the monetization layer of generative AI, and stable value on top of Bitcoin liquidity. And so how do we accelerate that? How do we get there a lot faster? We'll walk through a couple examples here. The first is we need more mints. So you can go on Bitcoin mints and you can see there's roughly 20 public mints. But we need bigger, more scaled, and trusted mints. And importantly, we need more distributed mints. We have to make it really, really easy for anyone to run their own mint privately and simply. We need more multi-currency mints. We have dollars, euros, and Bitcoin today, but we need more currencies, especially in the remittance corridors, like the example I walked through. We need more on-ramps. Mints currently only accept Lightning, but most of the on-ramps are on-chain Bitcoin. And so we need more mints accepting on-chain, and we need more exchanges accepting Lightning. And this is, I think, one of the largest unlocks for ecash. It needs to be this easy for you to use ecash. You should be able to use Apple Pay and load your ecash wallet. And finally, we have to build awesome products. This is what we're doing at Boardwalk. And this is what we're all doing in this room and really why we're all here. And it's early, but I think we have the opportunity to build something very special for the world and power the payments infrastructure for the next generation of these consumer products. Thank you.
Can you maybe explain how stablemin works? Because one of the use cases is stablecoins, but if I have an ecash denominated in dollars, so how does the mint behave? Like, what's the underlying asset there?
Yeah, so you could do it a few different ways. So there's two ways that I've seen. One is sort of the simplest way is you just take the Bitcoin in, you convert it to the currency, and you put it in a bank account. So you would just be receiving Lightning. As soon as you receive the Bitcoin in, you sell the Bitcoin for dollars, and you just hold dollars. So in that case, it's always stable, and you're always pegged one-to-one with dollars. There's also the concept of stable channels, and so that is where you're posting collateral in a Lightning channel, and it updates based on movements in exchange rate. So those are the two that have gotten the most traction. I think those are the two ways, the few mints that have both dollars and Bitcoin. I think that's how they work today.
But the first approach, it doesn't have this liquidity requirement or advantage, right? Because once I have put my money on an exchange and the exchange says this is no longer yours, then I have lost liquidity.
Right, you're trusting the custodial mint. Yeah. Mm-hmm.
And about the stable channel, is that how it's called? Like.
It's called stable channels, and you're always trusting the mint. So unless I think there's some cool ideas around of how to minimize that trust, but today it's like 100% custodial. So whether it's a stable channel, or you're holding money in a U.S. bank account, like you're trusting the mint to operate.
Yes, but there is a difference because if the mint is holding money in a bank account, I'm not trusting only the mint. I'm also trusting their bank.
The bank, yeah. And in the stable channels, you're trusting the mint, and then you're trusting the underlying technology of stable channels that it's working appropriately. Yeah, there's lots of trust required. It is custodial. Yeah.
Thanks.
Good point.
Hey, you mentioned that one of the things that we can do is make it as easy as possible for anyone to run and spin up a mint. Have you thought about the implications that might have on deteriorating what could be like the quality of the network? If you make it so easy that somebody who maybe isn't technically capable, maybe an Umbrel user or a hobbyist, just spins up a node and then they don't keep up with it, they're not able to troubleshoot it, this node could potentially be custodying users' funds. So that's different than just spinning up your own Nostr relay. There's less of a risk to other people. So I guess my question is, do you worry that by making it super easy for anyone to spin up a mint, it could at this stage make the quality of the ecash networks feel less reliable, less robust, because these low quality mints could be spinning up that people don't have the ability to maintain or troubleshoot?
Yes, for sure. And that's a great point. We actually, at Boardwalk, spent about 2 months building software to allow people to easily run a mint on their own. And we ended up not ever announcing it or launching it because of that exact reason. In like testing, like, I don't know, my internet went out of my house and then like my mint didn't work, right? And so the technology to make it that simple, I think, is not yet there. It will get there. So there's a ton of really interesting things people are working on to ensure that the mint doesn't go down. So I think that's one. We thought a lot about that. I think there's a lot of really interesting ways it can be done, but we're like not exactly there yet from a technical standpoint. The second point is you can, the Cashew protocol is working on authentication. And so you can and will be able to soon have a mint just remain private. So if it was like me and my friend that wanted to use the mint, it could just be the two of us. It wouldn't like get posted on bitcoinmints.com, and even if it did, you wouldn't be able to access it. And so in that way, it will limit having some like 1,000 people come on your mint, all of a sudden like overloading your Lightning node. You can just limit it to people that you know. Yeah. But that's like the mint piece is the distributed mint piece specifically is a huge unlock, I think.
Hi, thank you for this very insightful presentation. And I was wondering, do you know of any regulatory challenges around running a mint?
It's still really early, so yes, there probably are, and they need to be figured out. The depends on the jurisdiction, and then it depends on this technology that I talked about that we need to build. It depends how that's built, and that's why it's crucial we do it in a very distributed, private way. Yeah, but it's like completely like early. So yes, the answer is like yes. There are like a bunch of things you got to think through, but I don't think anyone's.
Do you know of an expert in this field currently, or someone that's very good to talk to regarding this?
Yeah, there might be people.
So you've I mean, as everybody stresses, right, that ecash is custodial. I'm wondering what the implications are when the context shifts in the way you're suggesting it probably will. So, you know, away from Bitcoin nerds who I would guess, I don't think this is that controversial, you know, usually the amounts are quite small and usually they're doing it for ideological reasons. If it goes to tens of billions of dollars of payments flow, the reasons are clearly commercial, the amounts are clearly pretty big.
Yeah.
That then, you know, it's not just like, oh yeah, okay, it's custodial, that's fine. It becomes like a massive financing question. That risk needs to be financed. So very open-endedly, do you just have any thoughts about how that's likely to happen? And maybe more interestingly, are there technical implications for Lightning about, or
Yeah.
maybe Bitcoin on chain about how to allow for financing that?
Yeah, for sure. And that's the point I made about it's not ecash alone. Like ecash needs Lightning needs Bitcoin, and when one gets better, they all get better. And so Lightning absolutely has to get better if this like AI payments reality is going to happen. Ecash gets you scale, gets you 100x, 1000x, 10,000x scale, but we ultimately need Lightning to also improve in order for that to happen. I think what ends up happening is potentially it really depends on like the mint and how the mint ecosystem evolves. And so you potentially have like either like larger mints that are run by service providers, larger mints that are run by well-known Lightning providers that can provide that Lightning infrastructure to run on. Is how it eventually evolves. I don't think it's like, you know, me or you in our house like running our Lightning node, like powering like $10 million of AI payments. Maybe the remittance use case, that's how it works, and that could like really scale and be really powerful. But for a single company running millions of dollars of payments every day, it's going to need a scaled Lightning custodian. So probably larger Lightning custodians or providers like Lightspark or Strike would have that infrastructure as well that they could offer mints or offer service providers to do that for them. But I think the like actually running a really like large, well-known, trusted mint is a huge opportunity. I mean, take a look at the stablecoin guys and the stablecoin custodians, and like Tether made $10 billion in the first 6 months of this year. Like that's insane. Stablecoins should be on Bitcoin for all the reasons I talked about, and whoever can unlock that using ecash has an enormous revenue opportunity.
Just a comment, actually, Bob. I think the key point in your presentation was when you assumed that we need on-ramps for that. So the real crucial thing to escape the regulatory and political capture is to remove the on-ramp element, which requires that Bitcoin stabilizes, which you mentioned, explained to everybody here, is not really very good when you try to spend Bitcoin at merchants.
Yeah, I'm actually excited about like the potential for more decentralized trading of Bitcoin on chain. Of Bitcoin not on chain. So whether that's using potentially ecash to do it, but that's like one area I think about all the time, but I have no idea what the answer is of how we do more decentralized Bitcoin trading, other than like what people proposed 10 years ago, which hasn't really scaled at all. But that, I think that's like a big unlock. If you don't need to use Apple Pay, and you can do it, the like, UX has to be good though. But Apple Pay's like amazing. Everyone knows how to use it. It's really good. Ideally, we can figure out a way to integrate that first, and then longer term, I think there are more advanced technical solutions to figure out how to do decentralized Bitcoin trading without on-ramp providers.
That was a fantastic presentation. Thank you. I just want to make a comment on also the previous question asked. I think it's useful to think of ecash system not specifically as global payment system where each mint needs to be able to serve everyone's use case at all times. When you remove that assumption, you can see many more realistic use cases today, also in line with our understanding of the regulatory frameworks around us, meaning that you can imagine an AI company running a very specific mint for only very specific task, and their requirements are, for example, scaling in that case, and they want to be able to unlock that insane scale. So, the TikTok example that you gave is also, I think, very informative. You can buy these magic shitcoins tokens there. This is probably a MySQL database in the background, and in this case, I'm specifically not sure, but I don't assume that TikTok applied for an e-money transmission license for enabling, small gift feature inside their application. So I think, when you start putting things into a smaller context and smaller context, then you can see way more clear how you can get forward with this without risking too much.
Yeah, that's a great point. There's like very specific, you don't need like the mint that runs everything and all these use cases and works for every company. Like you can get very, very specific into specific use cases, and leveraging you can pick one feature of ecash like really fast, and it could be one service provider that's just doing something really fast but gets the benefit of having the Bitcoin network effect. And like all the benefits of paying with Bitcoin, like there's no fraud and no chargebacks, which is like really big. Even for like the TikTok example, they still have like a ton of fraud that they have to manage, and they have like a massive payments team that works everywhere globally with every single payment method. And if they used Bitcoin and they used ecash, they wouldn't need any of that because it would all happen programmatically with no fraud. Cool. Thank you.
All right. Thanks.
Yeah. Oh. Well, it's gonna mute. Yeah.
Testing. Ladies and gentlemen, I hope you're all enjoying lunch. We will be beginning the afternoon very shortly. A talk here from Nothing Much in a couple of minutes. We have added something to the schedule. So an announcement at 3 o'clock downstairs. Thomas from Electrum will be doing a workshop on submarine swaps. So that's a new addition to the schedule at 3 o'clock. But yes, 2 minutes here, Nothing Much. Please get a comfortable seat.
He just went to the bathroom a minute ago.
Ladies and gentlemen, up next in the planarium, a man having spent a bit of time talking to this guy seems like an absolute genius, but he self-identifies as nothing much. Ladies and gentlemen.
Okay. That's the wrong screen. Sorry, I don't actually know how to move my windows without a mouse here. Nowhere key? Sorry, I should probably set up mirroring. Apologies for this. Okay. So, hi. So this talk is about blind signatures and anonymous credentials. I'm nothing much, as Walton said, or Yuval. Currently, I work at Spiral, so still working on CoinJoin stuff. That's basically what I've been working on forever in Bitcoin. Feel free to talk to me about that stuff offline. It's not what I'll be talking about today. Today, so David Chaum introduced blind signatures 40 years ago. And as far as I know, all the existing ecash systems still use some variant of blind signatures or something similar. So like the original DigiCash used this. GNU Taler uses, I think, RSA blind signatures. Fediment uses BLS blind signatures, and Cashew uses blind Hellman ecash, which is sort of the same thing. But I wanted to point out that there's like a lot of other ideas out there that I hope people here will find interesting. So, one sec, I just want to start a stopwatch. Okay. So, we're going to be looking at like some of the cryptographic building blocks. This is by no means exhaustive, and like we're hopefully by the end of this talk you have like a way of like a taxonomy where you can like choose the right ones for your use case if you have a use case. There's many links in the slides, so if you want to follow the links to like the original papers and stuff, scan the QR code or like it's on my GitHub. Oh, sorry. Okay, everybody seems to be finished. Okay, so the kind of the motivating example is like physical bearer tokens or assets or notes or whatever. This is like what Xiaomi ecash is trying to implement. So like just for the sake of a motivating example, like Alice goes to Bob and deposits like 1 unit of value, which could be like, you know, an atom of gold or whatever you want to, you know, some unit. And Bob gives her back basically a note that he can authenticate, that she or anybody else would have a hard time forging, that just says this is worth one unit. And if she comes back then and gives the note back, then she can get back her unit of value. Incidentally, like you can use these as payments themselves. Like that's what you know, cash represents historically. Unfortunately, in like computer stuff, if you like take a picture of such a note, then you can copy it as much as you like, and that doesn't work out very well for Bob. So Chaumian ecash approaches this by the RSA blind signatures allow Alice to so first Bob generates a public key, and this needs to be like well known. Then Alice comes along and does what's called a blind signature request. So she generates a random message. This is called a nullifier typically, or some other names for this are like serial number or key image. And the signature request does not reveal this message. So that there's like, it's completely obscured by like a random a value that's added to the signature request. So Bob doesn't see the value of this thing. But because he sees that a unit of value was deposited in whatever way, then he still decides to sign this. At the end of the protocol, Alice unblinds the signature, and she can verify that signature against Bob's public key. At some later point, she comes back, and she reveals the unblinded signature and unblinded message to Bob, who can see that this is a unique value that hasn't been used before. If that is the case, then he can give back the unit. So what the signature tells Bob is, I definitely gave out the signature previously. I only give signatures in exchange for deposits of actual units of value. Therefore, this represents a token, even though I don't know the specific request that this came from. Okay, so there's some practical challenges with this. So first of all, this is an online system. There's offline ecash as well. as far as I know, all of the offline systems always require some form of identity. So like if Alice double spends, she gets caught after the fact, and then you need some sort of like safety deposit or like a legal mechanism, some way of making things right after the fact. Whereas in online ecash, Bob is always a third party to transfers. So if Alice wants to transfer 1 unit of value to Carol, then like Bob is an active participant in this protocol. Like Alice needs to burn her original token, and Carol needs to request a new one in its stead. And there's no way for this to be secure unless Bob is actively reachable. So like all parties need to be online. Another issue is that the nullifier set basically grows indefinitely. So like practical systems need some sort of, or typically need some sort of pruning, which means you need to rotate the keys periodically. And then like you never really use just a unit, so typically there's going to be like 1 key per denomination. And this presents issues for privacy. So the proofs of unlinkability for blind signatures, they make sense for a single blind signature, but it does not follow that a batch of unblinded signatures made by different keys is unlinkable with respect to the original requests. Like that's a much trickier thing to like assert in a rigorous way about a private ecash system. And also like for like when you want to make a payment and you want to make it rapidly, let's say your balance is some value X and your payment amount is some smaller value than that. And let's say that you're using powers of 2 as the denominations. Well, what if the bits that you need to represent the smaller value are not part of the bits needed to represent your total balance? So you need to use perhaps some of the larger values, either split them, and maybe you want to do this ahead of time, and then there's a question of like, okay, well, how many of each denomination do you keep around? Or if you do this like just in time, then are you leaking even more information about the balance that you have? So yeah, the point I'm trying to convey here is that blind signatures or their various variants are perhaps not the ideal way of building these systems. Okay, so what is a blind signature really in this situation? It's a communication channel from Bob to Bob that conveys that the token, the unblinded value is was indeed issued in relation to a valid deposit. So the key thing to point out in this, thanks. The key thing to point out about this like communication channel notion is that the signed message is not the message that Bob is sending to himself. Rather, it's the presence of a signature at all that's communicating the information. And like for software people, you might know this as a unit type. So like a type that only has 1 possible value, and because there's only 1 possible value, you can't really encode any meaningful message in it. So slight historical digression here, but Chaum also described, I think like 10 years after the original blinded signatures paper, what's called digital credentials, which still use blind signatures, but the idea there is that the message is now not just like a random identifier, but it's potentially meaningful. So for example, Alice might have a passport and she makes a message like, I'm a citizen of country X, and if she convinces Bob that this message is valid, and gets him to sign, then at a later point she can show anybody, look, I have a message that's signed by Bob that says I'm a citizen of country X, and if you trust Bob, then this is as good as a credential. And interestingly, these don't need to have identity, unlike paper credentials. Like they're the authentication of Alice's identity is kind of decoupled from the underlying message. You still need to do it somehow, but in his original conception, like the goal is that these messages are not identifying. And how does this work in practice? Well, he just posits some sort of trusted party that both Alice and Bob trust. So Bob trusts this party to actually verify the messages before Bob signs. And Alice trusts the verifier, the third party, not to reveal the message to Bob so that her issuance request is still unlinkable to the use of her credentials. We can think about, like, what about if we encode a numerical value in these messages? So, like, this doesn't really work for the original idea because after you reveal the value, like, it still has a relatively high entropy. Like the degree to which a unique balance is going to be identifying is much higher than like one of many fungible units. Again, a decade later, Stefan Brands published his like PhD thesis in a book that's freely available online. And the idea there is to, instead of using a trusted verifier, we can still have something like blind signatures, but we can restrict the blind issuance, much like in the trusted party. And we do this with like zero knowledge proofs. And we also have like some way of selectively disclosing what is revealed. So the message in this case is not just a string, but something that potentially has more structure, like maybe a Merkle tree that you can reveal only a subleaf of, or yeah. Also of historical interest, slightly later, several signature schemes were proposed that tried to do this stuff a little bit more efficiently. In Brand's original work, there's like a gap in the security proofs. So these works kind of try to address that. Sorry, okay. Okay, so show of hands, who here is familiar with, or would say that they understand Schnorr signatures, not the blind variant? Okay, that's pretty good representation. So blind signatures, blind Schnorr signatures are kind of broken. Maybe you've heard of the Wagner attack or the Ross attack. But the idea there is when you have multiple concurrent blind signature requests, the requester is able to do this maliciously in a way that lets them forge signatures later. RSA and BLS blind signatures don't have this problem at all. BLS is also what's used by Fedimint. It also supports threshold signing. So I would implore you to like look at these more if you're like still wanting to build a blind signature system. But there are fixes for the Ross attack on blind Schnorr signatures. So an interesting way of fixing it is using much more general zero knowledge proofs to basically do the same as Brand's credentials. Here the idea is you have a message, you hash it as part of the signing, and then in addition to the blind signature request, if you prove in zero knowledge information about the hash pre-image, for example, that it satisfies some constraint, then like this not only allows for signing structured messages, but also fixes the concern with the Ross attack. So can we use this to hide denominations? Hopefully from like this slide, the implication is that yes, absolutely we can, but actually making zero knowledge proofs that are efficient for pre-images of say SHA-256 is still kind of tricky, despite like tremendous progress since 20 years ago when some of these ideas were originally introduced. Okay, so how would we more efficiently hide the values or hide the denominations that we're using? There's an old Bitcoin Talk post by Adam Back, which became the basis for confidential transactions. It's called Bitcoins with Homomorphic Value. It's no coincidence that Adam Back also implemented credlib. So, oops. Sorry. There we go. Credlib is an implementation of Brand's credentials. Microsoft later bought some of the patents on this and released a system called uProve. And already in Brand's thesis, there's some discussion of like how do you prove information about like numerical values that are committed to in the message. Kind of fun historical fact, apparently Adam Back gave a talk at Blockstream about this stuff, which inspired Jonas Nick to kind of look into this. He gave a talk at, I think it was Building on Bitcoin or Breaking Bitcoin in Lisbon in like 2019. And that was, like this talk is kind of trying to continue what was presented there. Yeah, I don't know what I'm saying about that, but so what does homomorphism mean? So you may have heard that fully homomorphic encryption is kind of like a unicorn. Here we have a much weaker requirement, which is just additively homomorphic. So the idea is if you have a function that is linear in its arguments, sorry, I keep pressing the left arrow and advancing the slides. So like if we have a function where we can add the values in the range of the function, so f of a plus f of b, and we can also add the values in the domain of the function, so f of a plus b, and these are the same thing, then that function is homomorphic. For committing to numerical values to be used in like economic transactions, a concrete version of F that we would care about is Pedersen commitments. The reason being that they not only respect homomorphism, but they also hide the values. Okay, so to look into that in more detail, we're going to do a brief refresher on like the algebra of this stuff. Please interrupt me if this is not clear, because like, yeah, my goal is to get you guys to, I guess, believe that this is not magic, and yeah, to try and demystify. So a group is a set G associated with a binary operation. So this is some function from elements of G to elements of G, pairs of elements to G to elements of G, where for every possible values in G, you can always apply this function and get another value which is still in the set. So that's closure. There's also a unique element in the group called usually the point at infinity. You can think of this as a kind of zero. So for every element in G, if you add O or 0 to G, then nothing happens. Groups also have inverses. So whenever you have any element A, there always exists some other element B, typically written as like minus A or A to the minus 1 if it's a multiplicative notation, where if you add them together, then you get 0. And finally, there's associativity, which for our purposes doesn't really matter, but so if you have 3 elements, the order in which you add them up doesn't matter. Like you still reach the same value eventually. Some more properties that are not, so like these are the group axioms, like this is what defines a group, but there are additional properties that are not shared by all groups. So the ones I'll be focusing on is abelian groups of some prime order. Abelian means that the group is commutative. So for any two values A and B, A plus B is the same as B plus A. There's also, so if you take a single point, G in this case, and add it to itself multiple times, well, that's typically represented as multiplication by a scalar. So a scalar is just like a normal number. Integers in general work. Even though these groups are finite, it behaves a little bit like modular arithmetic. Groups of prime order have no subgroups. We're not going to talk at all about subgroups, but just be aware that for like some of the fancier stuff that comes later, you do need a different setting, like pairing friendly curves, which have like typically have subgroups. But in this context, like if we have an abelian group of prime order, it's also a cyclic group. This means that if you have just one element in the group called a generator, you can add it to itself any number of times that you want, and eventually generate the entire group. And for prime order groups, this holds for every element other than the point at infinity. This is kind of important because like we're interested in, actually I'll come back to that in a second. Okay, so the last thing is that we're assuming that this operation is hard to reverse. So like if you add G to itself any number of times, and you give somebody else the result, and they know what you started with, and they know the result, it should be hard for them to figure out how many times you added G to itself. In multiplicative notation, this name makes a little bit more sense because it's like taking the logarithm. In Bitcoin land, we kind of usually stick to additive notation, so like maybe call it division or something, but the name is discrete log. Yeah, sec P256 K1, the elliptic curve used in Bitcoin is a group. Like it's a group where the elements are solutions to this equation, so they're pairs of numbers on a finite field. And there's an addition operation that's defined. We're not really going to look into that. But like if you add solutions any number of times, then you have these kind of nice properties. Okay, so still we're like building up to committing to values. So if we have a generator G, so this, again, can be any point on SecP 256K1 because it's a prime order cyclic group. Then Pedersen hashing is just like you take a message, A in this case, and you multiply G by A. You should know this as a derivation of public keys. And it's also known as Pedersen hashing because this is, it behaves a bit like a hash function. If you extend this slightly, so now we need two generators, and we need to make sure that the discrete logarithm of either generator is not known with respect to the other one. So like nobody knows a k, like some integer, that if you multiply g by k, you get h, or if you multiply h by k, you get g. The typical way of generating these is you take like a traditional hash function, you hash some string that's agreed to ahead of time, and use that as the x coordinate in the like elliptic curve. And if it's not a valid point on the curve, then you either shift it or try again. These are usually called nothing up my sleeve points. Okay, so if we have two of these generators, and we want to commit to a message M, so the first thing that we do is we pick a blinding term. So this is just a random value. and we multiply one of the generators by this random value and the message by the other generator, and add these 2 points together. So this is like adding salt to a hash. The idea is like even if some other party knows M or is able to guess M, the randomness makes it hard to figure out what the commitment is actually committing to. Maybe I'll skip this technical distinction. It doesn't really make sense. Or it does make sense, but okay, so in order to open this commitment, so like if you declared at a prior point, I'm committing to some value, here is the hash or the Pedersen commitment to that value. Later you can just reveal the pre-image to this commitment scheme and everybody knows that yes, you actually committed to that value, as long as you can't break the discrete logarithm problem on that curve. However, in this setting, it's not, like commitments are generally not going to be opened. Okay, so now we have all the elements of confidential transactions. So this dates back, I think, to 2014 or 15, deployed on Liquid, and is like the direct descendant of Adam Back's post. So the idea is like, let's say we have 2 numerical values that we need to use in a transaction, and these are, those are integers that we multiply the generators by. And suppose that V1 represents the value of a single input to some transaction, and V2 represents the value of a specific output. Then through the homomorphism property, so here just for clarity, I've written the group addition as like circled plus, because there's both scalar field addition, even though it's written with a minus sign. And it doesn't fit on the slide, I'm sorry. Okay, so the idea is we can take the commitments, so these are the 2 commitments, and subtract one from the other, and that is the same thing as a commitment to V1 minus V2, and here what's sliced off the slide is R1 minus R2. So if you know both R1 and R2, you can compute R1 minus R2, and in the case that V1 and V2 are equal, that's all you need to know to like open this commitment. This is effectively becomes a commitment to 0. And note that this, to prove that a given Pedersen commitment is a commitment to 0, you can make a proof that's basically just signing with C as a public key. And if the generator H is the same generator as used in the digital signature scheme, then this is literally the same. Like literally a standard signature, ECDSA or Schnorr or whatever will like be a proof that this is a commitment to 0. Why is that the case? Because the other generator is multiplied by 0 and gets canceled out of C. And it doesn't even need to be 0 necessarily. So as long as everybody knows what value something is trying to commit to, in confidential transactions, this would be like the generating like a negative value, effectively. For this, we need range proofs. And the meaning of range proofs in this case is V is small and congruent to like a small positive integer. Okay, so another show of hands. Who here claims to understand some kind of zero knowledge proof, any kind? Okay, so that's decidedly less than the previous poll. So if you did not raise your hand right now, but you did raise it before, I will try to convince you that you're wrong. So the most basic zero-knowledge proof that we can kind of think of is what's called the Schnorr identification protocol. For like a weird historical reason I don't understand, these are called sigma protocols because like apparently sigma is supposed to look like a Z or something. In our setup, the prover knows a secret. So this is analogous to like the private key, and publishes the image of this secret, so like the public key. And the prover wants to demonstrate to some other party, the verifier, that they actually know X, the discrete logarithm of P. So the first thing that we do is we generate a random nonce, and we multiply that by the same generator and send this commitment to the verifier. This should look very familiar. The next thing that happens, so this is an interactive protocol as described in the literature. The verifier generates a random challenge value, which is another scalar, and sends that to the prover. And then given this challenge, the prover can respond. So it's a fairly simple calculation, exactly the same one that's used in Schnorr signatures, not by coincidence. They send this response back to the verifier, and then the verifier can confirm that if you take the response times G, it should be equal to the original like nonce commitment R minus the challenge times the public key. Yeah, for completeness, here's like why this works. So this three-tuple RCS is known as the transcript for this protocol. And if the equation here is satisfied by this triple, then it's called an accepting transcript. So like a verifier who sees this should conclude that the prover actually knew X. And Schnorr identification is what's called a sigma protocol. So there's three properties that really matter. The first is called special soundness, or typically completeness is given first. But here, this will be the first. You've probably heard that nonce reuse is like a big no-no with Schnorr. The reason for this is that nonce reuse is what makes this a proof of knowledge. So if we have two transcripts, both with the same nonce, but two distinct challenges, then if you subtract the responses from each other and divide by the difference of the challenges, so division here is like computing the modular inverse on the scalar field. So not really division, or I mean it is, but yeah, I found that a little bit confusing at first, but basically you're able to, I should say this is not the inverse, or sorry, not the additive inverse or the negative, but the multiplicative inverse. So if you're able to do this, which you should be able to, for two accepting transcripts, then you should be able to compute X and extract it from these transcripts. And because the prover leaked, like by making this mistake, the prover has actually leaked the secret to you, if you have only one accepting transcript and nonce reuse did not happen, but you know that should it happen, you would be able to extract the secret, this means that the prover definitely had to know X in the first place. So this property is called special soundness. The other property is what's called honest verifier zero knowledge. So honest verifier, you can kind of ignore that. That's just to say, like the verifier will be following the rules and not trying to behave maliciously. In this situation, so there's this concept called a simulation. So if you generate a response and a challenge completely at random, you can trivially compute R for any public key. The key thing to notice here is that the simulator in this case doesn't know the discrete logarithm of neither P nor R. So because anybody can do this, anybody can generate a transcript that matches, that is accepting. And this kind of seemingly contradictorily implies that an accepting transcript has literally no information about X. The key difference is the order in which things happen. So if first you commit and then you challenge, then soundness holds. But if kind of time flows backwards, then a transcript reveals literally nothing about the message. The last property is completeness, which I'm not going to dwell on, but basically, there shouldn't exist any public key for which a prover who knows the discrete log cannot generate an accepting transcript. And if we just add hash functions through the Fiat-Shamir transform or Fiat-Shamir heuristic, this should be very familiar. Then essentially the prover can simulate a verifier and do this in such a way that anybody else could be equally convinced that the transcript is actually valid. The last element of signatures constructed from Sigma protocols is that you just add the message to be signed to the hash. So hopefully I've convinced everybody who raised their hands before that they actually do know a kind of zero knowledge proof. This is much more general than just proving the discrete log of a single value. So there's this notation here that for Schnorr identification, this is describes the meaning of a zero knowledge proof that is Schnorr identification. So here in parentheses are the inputs to this, and on the right side is a statement that's determined a priori. And in this case, this says X is a private input, P is a public input, and the statement is P is equal to X times G. So we can generalize this in two ways. The first is what's called a Chow-Peterson proof or discrete log equivalence proof. So if you have 2 points, P and Q, that are both the X times 2 different generators, then this proof shows that X is indeed the same for both of these. Another proof is the opening of a commitment. So if you have an X and an R, two private inputs that are not revealed, and C, a Pedersen commitment, then this proof demonstrates that C is indeed a commitment that the prover knows how to open. It does not reveal X and R. Okay. Of course, you can combine this, so you can generalize in both dimensions. And there's an open question here, which is can you do, if W1 or the witnesses here, the secrets, were generated according to Musig or Frost, can you does that hold for threshold proving? And it seems that it's very simple to do, but well, the security proofs are not simple at all. So there's yeah, good work to be done there. Okay, so very quickly, I'm kind of running out of time, but we can do a lot of interesting things just with this very basic zero knowledge proof. So can we prove disjunctions or statements? So yes, that's called ring signatures. Can we prove that something is a bit commitment? We can do that with OR proofs or without, with this like cute polynomial trick that I don't have time to go into. That in turn lets us make range proofs. So you can think of range proofs as a proof that a Pedersen commitment was constructed by summing denominations. And the way this works is you scale individual bit commitments by the denomination value and add them together. So if all of the constituent, the scaled commitments were bit commitments and the overall value is the expected commitment, then this shows that the value was constructed out of no more than log 2 of the maximum value of bits. And you probably have heard of bulletproofs or compressed sigma protocols. So these are like a fancy way of like doing even more. So all of this comes from essentially the same thing as the Schnorr signatures. The reason we need other zero knowledge proof types is because those are not always efficient. Okay, I'm going to skip blind Diffie-Hellman cache. The key point here is that to make that secure, we need discrete log equivalence proofs, which we, in theory, just covered. I have like 2 more minutes, right? Or not even. Okay. So very, very quickly, how do we make a blind signature scheme that is friendly to Pedersen commitment messages? So one way, it's not exactly signatures, but MACs, and specifically algebraic MACs. You can think of these as like an analog of like if Pedersen hashing is the elliptic curve way of doing hashing, then algebraic MACs are kind of the elliptic curve friendly way of doing like HMAC or something. And the system I'm most familiar with is the signal credential scheme. So in this case, what you do is the Bob, the server, provides an algebraic MAC on a Pedersen commitment. And Alice, the user, will just prove that she has a MAC. So not going to go into this, but instead of like revealing the MAC, she just makes a simple Sigma protocol proof that demonstrates that she has one. With a discrete log equivalence proof, she can generate a key image, and that prevents double spending. And this combination of the signal credential scheme with homomorphic value commitments is exactly what went into Wabi Sabi. So again, I'm gonna kind of blitz through. Wabi Sabi or signal credentials are keyed verification, so they're not publicly verifiable, but coconut credentials give you basically the same thing in a publicly verifiable and threshold friendly way. There's a proof of concept by Yasha from Fediment that you might be interested in. This has been applied, so there's Facebook or Libra DM produced like a series of systems that use coconut credentials to create a very nice sort of ecash-like system. We can also, instead of anonymous credentials, rely on ring signatures. So ring signatures are OR proofs. So if you know, like you don't even need a validator to give you a credential in some circumstances. This is the basis for like privacy preserving blockchains. Adam Gibson's curve tree like proving system is very nice and should be of interest to people here. There's also like super crazy stuff like divisible ecash. There's like mercurial signatures that give you delegatable anonymous credentials. So basically there's a ton of like really exciting research. I'm sorry that I didn't like kind of rush through the last few minutes, but hopefully I've convinced you that there's a lot of potential out there, and that, well, if simple anonymous credentials and homomorphic value commitments are not magic, then all of this like fancy stuff is not magic either. And yeah, like these are sort of the properties that I in my head I kind of organize all these building blocks with. Yeah, sorry for going over time.
Are the slides online?
Yes. Sorry, I forgot the key to go back to the first slide. If you, yeah. Cool. Yeah.
Thank you for the talk. It's been a treasure full of references and information, so I'll be getting back at it. You mentioned quickly that in the KVAX, I think it was in the KVAX scheme, one of the credential schemes, that a DLEQ proof must be provided in order to compute the nullifier. Can you expand on that? I don't understand why that's necessary.
Do you mean like, it's essentially the same thing as with blind Diffie-Hellman ecash, because only the prover can verify the algebraic MAC. Alice, in this case, doesn't know that it's a valid MAC and was produced by the previously announced public key. So in the signal credential scheme, the private key is like a 5-tuple or 4 plus n, depending. So this, like when she receives this T and V value, which is the algebraic MAC, Bob also gives her a zero knowledge proof that the V value corresponds to his previously announced public key. It's basically like in blind Diffie-Hellman ecash, the same thing. Cool. Okay. Thanks.
I'm looking at screen settings. Welke moet ik hebben? Welke settings moet ik hebben? Test. Should I wait or can I go? Yeah? Okay. Hi. This talk is going to be a lot less into the weeds as the previous one, so don't worry about it. I even have some pictures of dogs. I think we have enough cats in Bitcoin, right? So yeah, I'm Steven. I work on ARC at a company that we recently announced called Second. And I've done several talks explaining ARC. I'm not going to go too deep into the weeds, but I'm going to have time for questions if people have specific technical questions afterwards. But I'm going to try compare ARC with ecash. There's a lot of confusion often from users who think that it's very much like ecash. It's not too much like ecash, but there's actually some similarities and a lot of differences. I titled the slide the presentation "Enemies or Friends," but obviously friends. I mean, we're all Bitcoiners. So what is ARC in a nutshell? ARC is a new second layer protocol that instead of working with channels like Lightning does, it works around the concept of sharing UTXOs with multiple users. So there's a coordinator that we call the ARC service provider, and he's gonna orchestrate what we call rounds. And the results of these rounds will be a UTXO on the blockchain that is sharedly owned by a bunch of users. And the shares of these UTXOs we will call virtual UTXOs or VTXOs. And then the ARC protocol and these rounds allow for users to atomically exchange these VTXOs for other VTXOs. So it's like an atomic off-chain transaction protocol. The trade-off of the VTXOs is that they have an expiry time. So something around the order of magnitude of 30 days, the VTXOs expire and you need to come online to basically send them back to yourself to get a new fresh VTXO with a new fresh expiry time of 30 days. Person-to-person transfers can kind of happen without having to participate in these rounds. We call them OR-core, like out-of-round transactions. So you can basically directly pass on a VTXO to some other user, which happens instantly. And then now the VTXO is owned by this other user, and then he can either enter the round to refresh it for a new one, or he can just wait until the expiry goes down and then refresh it for a new round. So obviously I have to have a slide